We present SUDS, a method for building scalable 3D representations of dynamic urban scenes. We extend neural radiance fields to build 3D representations of large-scale dynamic scenes using input videos taken at different times. Prior work tends to reconstruct single video clips of short duration, as existing methods often scale linearly with the number of moving objects and input videos. In contrast, our method can be scaled to thousands of objects across millions of frames spanning geospatial footprints of hundreds of kilometers. To our knowledge, the largest dynamic NeRF representation built to date. As a mega-NeRF, we scale our method by dividing the scene into multiple cells and train a separate representation for each in parallel. Since conventional NeRF training of MLPs is computationally prohibitive at our target scale, we instead use hash tables within each cell. Each cell's representation factorizes the scene into 3 branches: a static branch containing non-moving content consistent across videos and time, a dynamic branch to disentangle video-specific objects, and a far-field environment map used to represent faraway objects in the sky. Each branch uses a multi-resolution hash table followed by a small MLP. The static branch makes use of 3D spatial voxels, while the dynamic branch uses 4D spacetime voxels. The far-field branch uses voxels representing normalized 3D direction vectors that index an environment map. To allow otherwise static content, such as buildings or vegetation, to change appearance across videos, we further condition the color predictions of our static branch on a latent code based on time and video. We use a 3D warping loss consistency term during training to model movement between observed frames. We supervise this loss entirely of unlabeled inputs, most notably sparse 2D correspondences extracted from Dino. We also directly distill the Dino features into our representation and minimize both the photometric and feature metric loss of warped renderings relative to the ground truth inputs. Our trained representation is suitable for a number of downstream tasks, including semantic segmentation, focal length manipulation to mimic fisheye lenses often used for near-field detection on autonomous vehicles, and dynamic object removal. Please refer to our website for more details.